Okay, hi Zach. Welcome to lesson number 70. This starts on page 284. I think you're really going to like this one, and I'm actually very glad for this lesson because this is a little bit of a change of pace. We're not going to be factoring quadratic equations. We're not going to be doing that kind of nonsense. Well, maybe you are a little bit in your homework. I'm sure you probably will. But speaking of probably, we're going to be talking about probability. So it's definitely, we're switching gears here. And I think this is super fun. I love probability. I think it's very interesting. Here we go. We're going to start out with a comic. Look, these guys are about to joust each other or something like that. I think that's what it's called. But this guy's yelling, "Time out, please. Eyelash." Right? Speaking of probability, that has probably happened at some point, right? That would be the worst time in the world to get an eyelash in your eye. All right. So the study of probability is based on the study of outcomes that have an equal chance of occurring. So that's things like rolling dice. Okay, so this is, I learned this and you helped me with this. Die is singular, so one die, and two dice. Dice is plural. Okay, so it's just like, so the study of probability means that you have to have an equal chance of happening. So when you roll a die, there's an equal chance of any face coming up as long as it's a fair die. Same with a coin. As long as it's a fair coin, meaning it's not a trick coin, like there's not two heads on a coin. As long as it's a fair coin, then you have an equal chance of heads or tails, right? So there's a bunch of things happening like that, like flipping coins, rolling dice, selecting cards out of a deck, drawing marbles out of an urn. Okay, so we're going to look at some of those things and figure out how to find the probability. So in a fair dice, for example, each face should come up 1/6 of the time because, as you know, you can get the number 1, you can get the number 2, all the way up to 6. So what's the chance of getting a 4? It's 1 out of 6, okay? So the probability of each face is 1 out of 6. All right. It's customary, so this is a little bit of vocabulary here. It's customary to call activities like these, like flipping coins, rolling dice, blindly selecting cards from a deck, drawing marbles. These are called experiments. So it's the act of doing one of those things, right? Okay. And then outcomes are the results, the individual results that you get. So I'll write individual results. Okay, there's also something called a sample space. And the sample space is the whole set. You can think of it as a set of all possible outcomes. Like if you're rolling a dice, the set would be 1, 2, 3, 4, 5, 6. That's the set of, right? Because obviously you can't get a 7 if you roll it just one time. So that's the set of possible outcomes it could be. And that's basically what you need to know to do these probability problems or equations. So we define the probability of a particular event with an equation. When you look at flipping a coin, there's only two, the sample space is small, right? You're either going to get a heads or you're going to get a tail. That's the sample space. This is one outcome. This is another outcome. Here's the set for rolling dice. Okay, you're going to get one of those things. The probability of a particular event. So this is the equation that you need to know. And I'm going to just outline this in a thought cloud. It's the Pope equation. The Pope equation is the probability of a particular event. The probability of a particular event is the number of outcomes that satisfy the requirement. So these are the things you want to get. The number of outcomes that satisfy the requirement. Like, let's say you're about to win a game, but you're only going to win it if you roll a 6. And you want to know, what are my chances of getting a 6? These are the number of things that can satisfy the requirement. And on the bottom is the total number of outcomes in a sample space. Okay, so this is no sir on the top, and this is T-NOS on the bottom. No sir, T-NOS. Okay, and that's the Pope equation. The other thing is your answer is going to be somewhere between 0 and 1. So if you ask yourself, what are my chances of getting a 6, of rolling a 6 on a dice? It's either going to be 1 if you get it, or it's going to be 0. And it could be somewhere in between. Like maybe you have 2 dice and you can get there are different ways you could get to the number 6. Then your probability is going to be somewhere in between. If the dice doesn't have a 6 on it at all, your probability of getting a 6 is 0. If your dice has all 6s on every single face, it's not a fair dice, but still, if it has all 6s, then your probability of rolling a 6 is going to be 1. But if it has if it's a normal dice, your probability is going to be 1 out of 6, which is somewhere, I don't know, 1/6. Where would that be on this number line? If this is a number line from 0 to 1, it'd be like somewhere down here, right? Okay, and we could figure that out, and lucky for you, we are going to figure that out. So here we go. There are some things that might be impossible, right? So let's say you need a 7 to win, and you only get one roll with one die, D-I-E. What's your probability of getting a 7? Well, that's impossible. Thank you, Dwight. Dwight is right on this one. That would be impossible. Just like your probability of getting a -2, that would be impossible. Your probability of getting a 7.5, that would be 0. So if it's impossible, the probability is 0. Okay, so it's not possible. So the only probability answers that you're going to get are going to be between 0 and 1. And it's inclusive. It could be 0, it could be 1, and it could be anything in between. So that's the only answer you're going to get for probabilities. It's somewhere between 0 and 1, inclusive. Okay. So you're telling me there's a chance. I know you've never seen that movie, but that's all right. Someday in the future, you'll get that joke. All right, example 70.1. Let's look at it. It's on page 285. A fair coin. You've got a fair coin. Let's change colors. A fair coin. It's tossed 3 times and comes up heads every time. What's the probability that on the next toss it will be heads? Oh, don't fall victim to this blunder. This is why Vegas makes money, because people believe that if you get heads and heads and heads, they're wanting to know, what's this one going to be? So people tend to think, and it's human nature to think this, that past events have an impact on this, but they do not. These are independent events. So just because you got heads 3 times in a row doesn't mean, well, I'm bound to get tails because it's bound to come up, so it's more likely to come up. No, any single time that you toss a coin, the chance of getting heads is 0.5. The chance of getting tails is 0.5. And even if you get heads 3 times in a row, what's the chance of getting heads again? It's still 0.5. In other words, what has happened in the past does not affect any future events, as long as they are independent events. So the probability of heads on the next toss, I already know ahead of time before I even do the problem, is going to be 1/2. So if you want to be sure, let's do the problem. Let's do the Pope. The probability of a particular event is the number of outcomes that satisfy the requirement. So what do we put on top? Well, out of heads and out of tails, we want to know what's the chance of getting heads. So there's only one chance of getting heads because you've got one coin and one head on one coin, right? What is the chance of getting tails? It would also be one chance, right? One chance. And then on the bottom is the total number of outcomes in the sample space. The sample space is this. You could have heads or you could have tails. So there's two options there. So the equation tells you that your chance of getting heads is 1 out of 2. And that's the same as 1/2, which is the same as 0.5. Okay, let's do the next one. All right, just a little animation. Okay, it's kind of random which one you get out of that whole gumball machine, right? This is similar to a gumball machine. So example 70.2 says 6 green marbles, and I drew a picture with 6 green marbles there, and 8 red marbles, and I drew a picture. I didn't like equalize them out, but maybe you could shake the bag, or it looks like a bag, but it says it's an urn. Anyway, 6 green marbles, 8 red marbles are placed in an urn. 1 marble is drawn and then dropped back into the urn. The second marble is drawn and dropped back into the urn. Both marbles were red. Okay. If another marble is drawn, what's the probability that it's going to be red? Okay, this is, don't fall victim to this classic blunder. Your friends are going to fall victim to this blunder. If anyone you know is a gambler, they are going to fall victim to this classic blunder. But whatever you pull out in the past, as long as you put it back in, doesn't matter, does not affect the outcome. So let's just do the Pope equation, okay? Pope equation. So on the top is the number of outcomes that satisfy the requirement. So how many ways can you pull out a red marble? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 ways you could pull out a red marble. So 8 goes on top. On the bottom, it's the total number of outcomes in the sample space, TNOS, total number of outcomes in the sample space. So how many outcomes in the sample space? I already counted the red ones and I got 8. So now we're going to do 9, 10, 11, 12, 13, 14. There are 14 things you could pull out. So 8 out of 14 is the ratio that you get, the chances that it's going to be red. And you can simplify that further. Let's see, I'm going to divide that in... divide that in half. Yeah, so it's going to be 4/7. So the probability of pulling out a red one is 4 out of 7. So if you do it 7 times, you'll probably get 4 reds. But turns out that the more chances you do it, the more it's going to approach this ratio. So it'll be closer to this ratio if you pull it out 7,000 times. Like if you do this 7,000 times, you're likely to get 4,000 red. But if you do it 7 times, you're likely to get 4 red. Anyway, that's the probability. All right, let's do the next one. Example 70.3. This lady is saying, maybe, probably not. She doesn't strike me as someone that knows a lot about probability, so I'm just going to get rid of her. All right, example 70.3. It says a single die is rolled 3 times. The results are 1, 4, and 3. What's the probability that the next roll will produce a number greater than 2? Okay, so the first thing I'm going to do here is I'm going to disregard that these are independent events, and as long as they're independent events, everything they told me is irrelevant. Irrelevant. Doesn't matter. Only an idiot would think it matters. So then the next thing I'm going to do is I'm going to actually define my sample space. So I need to define my sample space. So sometimes this is a very important part of it. Can I get a 1? Yes. Well, first of all, can I get a 0? No, because I'm rolling it. I'm going to get one number, and it's either going to be a 1 or it's going to be a 2. It's going to be a 3 or a 4 or a 5 or a 6. Those are the only possibilities that it can be. So they want to know what's the probability that the next roll will produce a number greater than 2. So greater than 2, does that include 2? No, it doesn't, because 2 is not greater than 2. 2 is equal to 2. So what's my chances of getting a 3, a 4, or a 5, or a 6? Now I'm going to do the Pope equation. I get one roll, and I want it to be a 3, 4, 5, or 6. There are 4 ways I can get a number greater than 2. So on the top is going to be 4. On the bottom, there are 6 different things I could get. That's the whole sample set that goes on the bottom, okay? And then my ratio is 4 out of 6. So the chances are 4 out of 6, or 2/3 of a chance, or 0.66, right? There's a 66% chance that I get something greater than 2. Okay, those were pretty good odds. Yeah, it's pretty good. Alrighty, so let's do the next one. Example 70.4. This is so easy than your last lesson, right? All right, and this guy's saying, okay, but it's probably not going to happen. Well, let's see if it probably will or probably won't. That's what we're here to find out. It says, 2 dice are rolled. What's the probability that the sum of the number rolled is exactly 7? Okay, and then they want to know for B, what about a number greater than 8? I'm going to erase this for now and just focus on the 7 because that is hard enough. This problem is way, way trickier than you think, because if you have 2 dice here, right? You've got a dice and you've got another dice, and you want a number that is exactly equal to 7, but there's lots of different ways to get 7. You could get, right, you could have like a 6 over here and a 1, or vice versa, right? You could have a 1 here and a 6 there. Or you could have, so you could have a 1 and a 6, or a 6 and a 1, or a 2 and a 5, or a 5 and a 2, or a 3 and a 4, or a 4 and a 3, right? So there's a lot of different ways that can happen. And then what's the sample set? The sample set is all the possible combinations you could get with 2 different dice. So in order to figure that out, you have to make a table like this. So this represents the first dice. So you could have 1, 2, 3, 4, 5, 6 on one of the dice. And you could also, this represents the second dice. On the second one, you could get a 1, you could get a 2, you could get a 3, or a 4, or 5, 6. Those are independent from each other. It doesn't matter what one lands, it won't affect what the other one lands. So you could have a 1 and a 1, and you could get a sum of 2. You could have a 2 and a 2 and get a 4. Or you could have any of these random combinations, and they're random to the best of our knowledge, right? So what is the probability of a sum of 7? Well, once you make a table like this, it's a little bit easier because you can see that you can see all the different ways to get 7, which is basically what I wrote out before. You could get a 1 and a 6 and get 7 that way. Or you could get a 6 and a 1 and get this 7. You can get a 5 and a 2, 2 and 5, 3 and 4, 4 and 3. So these are all the different ways you could get 7 along this line. And then everything else is another option that you could get. So you can see how probability gets very complicated because there's a lot of options that it could be. So let's start with the probability of 7. And let's do the Pope equation. So the Pope is going to be a sum of 7 on top. How many ways can you do that? And then total number of possible outcomes. Total number of possible outcomes. That was number of outcomes in the sample space is what I want to say. Number of outcomes in the sample space. Okay, TNOS. So if we do the Pope equation, how many ways can you get 7? Well, I'm just going to cross them off, I guess. Let's do 1, 2, 3, 4, 5, 6 ways you can get 7. So I'm going to put a 6 on top. And what are the total number of in the sample space? Now that does include the 7s that we just counted. So it would be 1, 2, 3, 4, 5, 6 times 6. So there's 36 squares here. Any of those could happen. So it's going to be 6 over 36. So your chances of getting 7 to be the sum is 6 out of 36. And if you simplify that, it's going to be 1 out of 6. Okay? Okay, so that's the answer for the first part. Now, the second part of the question wanted to know, what's the probability of getting something that's bigger than 8? So that was this question down here. What's the probability of getting something that's bigger than 8? All right, this is tricky, but it's not as tricky now that we have this table all written out. So we can see all the ones that are bigger than 8. You've got a 9. All of these basically are greater than 8. Now notice that I'm not including the 8s because 8 is just equal to 8. 8 is not greater than 8. So let's use the Pope equation. How many ways can I get a number bigger than 8? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 ways I can get a number bigger than 8. And then the denominator is going to be the same. There are 36 different things that I can get every time I roll 2 dice together. 1 out of 36 every single time, okay? So the answer here is going to be 10 out of 36. And if I simplify that, because they're both even numbers so I can divide them in half, I get 5 over 18. So the chances, or the probability, of getting a number greater than 8 is 5 out of 18. That's the answer. Okay, now the second part of this lesson does also have something to do with probability, but so it's along the same line of thinking, and it's kind of interesting, I think. It says the probability of future outcomes of independent events happening in a designated order, so order is a key word, is the product of probabilities of the individual outcomes. So now it wants to know, what's the probability of getting heads and then tails? Now, getting heads the first time, it doesn't make a difference on what the second one is, but if you want to know the probability of getting heads and then tails, that's different than the probability of with just one toss. So if there are 2 tosses, then you're talking about a designated order problem. And this makes it a little bit more complicated, but it's actually interesting and easy to figure out. Because all you do is you find the probability of the first one, like the probability of heads, and then you find the probability of tails, and then you multiply them together. And that's what the answer is going to be. Okay, so for example, let's just do that. What's the probability of getting heads on the first toss and then tails on the second toss? So the probability of heads, we already figured this out, is going to be 1/2 because there's one chance out of 2 possible outcomes. The second one, the probability of tails, is going to be 1/2. Now, to find the probability of getting heads and then tails, you multiply them together. And the probability of getting heads and then tails is going to be 1 chance in 4. Okay? And then they prove to you that this is true with a tree diagram. So here's a tree diagram. And you're starting out here, and this is like as if you're going along in time. Time is going this way, okay? So like the tree is growing. So you start out here, and you toss a coin. And it's either going to be heads or it's going to be tails, okay? If it's heads, then you have another branching point because you're going to throw it again. Your second toss could be heads or it could be tails, okay? But you could have gotten tails the first time, and if you get tails the first time, then you could get heads again, and then you could get tails again. And so you can see that your chance of getting heads and then tails, you would have to go, let's see, you'd have to go this way. Oh, that doesn't show up. You'd have to go this way and then this way. And that is the probability we figured out, 1 out of 4. And that makes sense to me because this chance is also 1 out of 4. This chance is 1 out of 4. And this chance is 1 out of 4. And you have to do one of those 4 things, and that's why they all add up to 1. They add up to 1 because one of those things has to happen. The chance of one of those things happening is 1, right? The chance of any individual thing happening is 1 out of 4. And a tree diagram kind of shows you why that's true, okay? All right, if you don't understand this part, I want you to read it in the book on page 286, and they probably do a better job of explaining it to me. But if you have 2 tosses, then there's 4 possible outcomes. This is 1 possible outcome, 2, 3, 4 possible outcomes. So if we do the Pope equation, like right here, the probability of getting heads and then tails is the number that satisfy the requirement. So that's one of these. One of these will satisfy the requirement. And then the total number of possible outcomes is 4, because there are 4 different things that could happen if you toss a coin twice. So that's the answer of the probability of getting heads and then tails. And the key to remember is that if you want the probability of 2 things happening one after another, you multiply them together. So let's do example 70.5. A fair coin is tossed 4 different times. What's the probability of heads, heads, tails, tails? If you wanted that to happen and then it did happen, it would be like a Christmas miracle, right? So that's why I put that there. But he's a little distracting, so I'm going to remove it. So you toss a coin 4 different times. What's the probability of getting heads, heads, tails, tails? Now, let's do the Pope equation. And let's just look at one of these things. The probability of heads with 1 toss is 1/2. And the probability of tails in 1 toss is 1/2. So if you want to get heads, heads, tails, tails in that order, then you have to multiply all those probabilities together. So what's the probability of H happening, and then H happening, and then tails happening, and then tails happening? So the probability of H is this, 1/2. So I'm going to write 1/2. Let's do it with this right here. Now I'm going to multiply it by the probability of H happening, which is also 1/2. Then I'm going to multiply it by the probability of tails happening, which is also 1/2. Then I'm going to multiply it by the probability of tails happening again, which is 1/2. And if I want all the coins to go in that order, heads, heads, tails, tails, the chance of that happening is 1/2 times 1/2 times 1/2 times 1/2. And you can see that that number is getting a lot smaller. So the chance of heads, heads, tails, tails is 1 out of 16. Because there's a lot of other things that could happen, right? Maybe there could be a tail right there or a head right there that would mess it up, right? So you'd have to do it again. If you do it 16 times, you're likely to have it happen 1 time. That's what that is saying. All right, let's do example 70.6. Take a chance on me, right? You remember that? Okay, he was a singer. Anyway, the spinner shown is spun twice. So let's look at that spinner. If you spin it, let's say you have to say that you're not going to land right on the line, and that's going to be disqualified, right? So let's say you're either going to land on a 1, a 2, a 3, or a 4, and it can't be right on the line. So the spinner shown is spun twice. What's the probability of getting a 4 and then a 3? So let's figure out the probability of getting a 4 first. That's the Pope equation. There's only one way you can get a 4 because there's only one 4. But there's 1, 2, 3, 4 different things you could get. So the probability of getting a 4 is 1 out of 4. Same with the probability of getting a 3. There's only one way to get a 3, and there's 4 different things you could get. So that's the probability of getting a 3. Now, if I want to get a 4 and then a 3, I have to multiply those together. So it's going to be 1/4 times 1/4, which is 1/16. So if I want to get a 4 and then a 3, I'm probably going to have to spin it 16 times before that happens. I mean, not exactly, but chances are that the chance of getting a 4 and then a 3 is 1 out of 16. Okay, that's it, Zach. That's the lesson. First, I'm going to show you this. I'm glad you could join me today because it was a great lesson, even though you don't have a choice. And then here's the Far Side cartoon for today. And the word is anatidophobia. I'm pretty sure that that is a made-up word, not a real condition. But it says, the fear that somewhere, somehow, a duck is watching you. It looks like this man is suffering from anatidophobia or whatever. And he might have a reason, right? Maybe. Somewhere, somehow, a duck is watching him. All right, hope you have a great day, Zach. Love you. Bye.